Hello there, and welcome to the Deep Sleep Discoveries channel. Tonight, let your breathing slow as we drift outward into the quiet vastness of the universe. This is a place shaped by time, gravity, and light, unfolding patiently over billions of years. Nothing here rushes, nothing demands attention. Simply allow these gentle truths to carry you softly toward rest. Before we begin, if these calm, curious explorations help you unwind or give you a quiet way to end your day, please consider liking and subscribing to the channel. It helps others find their way here too. Now sit back and relax as we begin our journey through 100 astronomy facts. The universe is approximately 13.8 billion years old, a span of time so vast it stretches far beyond everyday understanding. This age comes from careful measurements of cosmic expansion and ancient light still traveling through space. Everything we see today, stars, galaxies, and drifting clouds of gas, emerged gradually from that long unfolding. Nothing appeared all at once. Instead, structure formed slowly, guided by gravity and cooling matter. When you look into the night sky, you are not seeing something new, but something very old, still quietly evolving. This immense age sets the rhythm for everything that follows, including the light that continues its journey toward us. Light does not arrive instantly from distant objects. It travels across space at a fixed speed, carrying information forward through time. When that light finally reaches Earth, it shows us the universe as it once was, not as it is now. Some of the glow reaching our eyes tonight began its journey before Earth even formed. Galaxies appear younger, stars less evolved, frozen in earlier stages of cosmic history. Astronomy becomes a gentle form of time travel, allowing us to look backward simply by looking outward. As distance increases, so does the depth of the past we observe, leading naturally to thoughts of just how much light fills the universe. There are more stars in the observable universe than grains of sand on all of Earth's beaches. Each tiny grain represents a comparison point for something unimaginably distant and luminous. Stars gather into galaxies, galaxies into clusters, and clusters into immense networks stretching across space. Most of these stars will never be seen individually, yet they exist nonetheless, burning quietly in the dark. This comparison is not meant to overwhelm, but to soften perspective. Vast numbers lose meaning at this scale, becoming more like a gentle background hum. Within that hum, entire galaxies slowly rotate, including the one we call home. Our Milky Way galaxy contains hundreds of billions of stars, bound together by gravity and moving in long, graceful orbits. From within, the galaxy appears as a soft band of light across the sky, but from afar it would look like a slow turning spiral. These stars vary widely in size, temperature, and age, yet they share a common origin in ancient clouds of gas. Between them lies space that seems empty but is threaded with dust, radiation, and magnetic fields. The Milky Way feels immense from our perspective, yet it is only one island among many, drifting within a much larger cosmic ocean. The Milky Way is only one of trillions of galaxies in the observable universe. Each galaxy contains its own stars, planets, and long history of formation and change. Some are large and orderly, others small and irregular, shaped by collisions and slow gravitational tides. They gather into clusters, drawn together over immense timescales, yet still separated by enormous distances. From far away, galaxies resemble scattered embers glowing in the dark. Their sheer number reminds us that no single structure dominates the cosmos. Instead, the universe spreads itself widely, unfolding in every direction at once, guided by expansion itself. The universe is expanding everywhere, not from a single center but uniformly across space. Galaxies are carried apart as the fabric between them stretches, gently and continuously. This expansion does not feel like motion through space, but growth of space itself. The farther away a galaxy is, the faster it appears to recede. This quiet stretching has been happening for billions of years, shaping the large-scale structure we observe today. There is no edge being approached, no boundary rushing outward. Expansion simply continues, calm and persistent, setting the stage for gravity to shape matter into stars within that growing cosmic arena. Space is not a fixed, empty container. It is dynamic, capable of stretching and bending under the influence of energy and matter. As the universe expands, space between galaxies slowly lengthens, carrying light along gently curved paths. This stretching affects how we measure distance and time across cosmic scales. Over immense periods, it determines which galaxies remain visible and which drift beyond reach. Yet, within this expanding space, local regions remain bound. Stars still orbit galaxies, planets still circle stars. Expansion governs the largest scales, while gravity quietly holds smaller structures together, allowing matter to gather and condense into luminous forms. Gravity is the force that gives the universe its structure. It pulls matter together, guiding gas into stars and stars into galaxies. Without gravity, the universe would remain a thin, drifting fog. Instead, gravity creates shape and rhythm, allowing collapse to balance expansion. Though it is the weakest of nature's forces, gravity acts across vast distances, patiently accumulating influence. Over time, tiny imbalances grow into massive structures. Galaxies form, clusters assemble, and cosmic patterns emerge. Gravity does not hurry. It works slowly, steadily, shaping the universe in a way that feels almost intentional, leading naturally to the birthplaces of stars. Stars are born inside nebulae, vast clouds of cold gas and dust drifting through galaxies. These clouds appear calm, yet within them gravity quietly gathers material into denser regions. As the gas collapses, it warms, forming glowing cores that mark the earliest stages of a star's life. Surrounding dust absorbs light, hiding much of this process from view. Over time, pressure builds until nuclear reactions ignite and a star begins to shine. Every star, including our Sun, once passed through this gentle transformation. These nebulae serve as cosmic nurseries, continuously renewing the galaxy with new points of light. The Sun is often described as an average star because it follows a stable, long-lived path on the main sequence. Yet compared to most stars in the Milky Way, it is larger and brighter. The majority of stars are small, cool red dwarfs that shine quietly for immense spans of time. The Sun occupies a comfortable middle ground, bright enough to warm planets, steady enough to last billions of years. Its balance allows life to exist without extremes. From this familiar star, we observe the wider universe, using its light as our reference point for understanding all other stars beyond. Stars shine by fusing hydrogen into helium deep within their cores. Under immense pressure and heat, hydrogen nuclei merge, releasing energy in the process. This energy moves outward slowly, taking thousands of years to reach the surface before escaping as light and warmth. The steady glow of a star is the visible result of this hidden balance between gravity pulling inward and energy pushing outward. As long as fusion continues, the star remains stable. This quiet process powers nearly everything we see in the universe, from starlight to the warmth that reaches distant planets, including the gentle light that supports life around stars like our Sun. Inside a star, two opposing forces remain in constant balance. Gravity pulls matter inward, trying to compress the star further, while energy from fusion pushes outward. This balance, known as equilibrium, allows stars to shine steadily for millions or billions of years. If gravity gains the upper hand, the star contracts. If fusion becomes too strong, the star expands. Most of a star's life is spent in this quiet middle state, neither collapsing nor exploding. This long stability creates predictability across the cosmos. Planets can form, orbits can settle, and complex systems have time to develop beneath the calm persistence of starlight. Some stars shine thousands of times brighter than the Sun, flooding their surroundings with intense light and energy. These luminous giants burn hot and fast, consuming their fuel at remarkable rates. Their brilliance can illuminate nearby gas clouds, shaping them into glowing nebulae. Despite their brightness, such stars are rare and short-lived. They blaze intensely, then fade quickly on cosmic timescales. Their powerful radiation influences the formation of nearby stars and planets, sometimes triggering new birth, other times halting it. These brilliant stars act as both creators and disruptors, leaving lasting marks on their galactic neighborhoods before their lives inevitably draw to a close. Massive stars live dramatically shorter lives than smaller ones. Though they contain far more fuel, they burn it at an astonishing pace. Their immense gravity compresses their cores tightly, driving fusion faster and hotter. As a result, these stars may shine for only millions of years, a brief moment compared to the Sun's long lifespan. Their short existence is intense and transformative, ending in powerful explosions that reshape surrounding space. In contrast, smaller stars live quietly, conserving their fuel. This difference in lifespan introduces a gentle rhythm to the universe, where brilliance and endurance balance one another across time. Small stars, especially red dwarfs, burn their fuel so slowly that they can shine for trillions of years. They glow faintly but steadily, conserving their energy with remarkable efficiency. Because the universe itself is younger than these projected lifespans, none of these stars have yet reached their natural end. They represent the long future of starlight, continuing to shine long after larger stars have faded. These quiet stars dominate the galaxy by number, filling space with gentle, persistent light. Their endurance ensures that even as the universe ages, it will not fall suddenly into darkness. When a star's supply of hydrogen in its core begins to run low, subtle changes start to unfold. Fusion slows, and gravity begins to gain strength. The core contracts and heats, while the outer layers respond by expanding. These changes happen gradually, often over millions of years. To an outside observer, the star may grow brighter or larger, entering a new phase of its life. This transition marks the beginning of stellar aging. The steady balance that once defined the star slowly shifts, preparing it for the transformations that follow. These changes set the stage for some of the most dramatic events in the universe. For some stars, the end arrives in the form of a supernova. This explosive event occurs when the star can no longer support itself against gravity. In massive stars, the core collapses suddenly, triggering a rebound that tears the star apart. For a brief moment, the explosion can outshine entire galaxies. Though violent, this process is not sudden chaos, but the final result of long, predictable changes. The supernova marks both an ending and a beginning, releasing energy and material into space. From this destruction comes the raw material needed for new stars, planets, and future systems. Supernovae are responsible for creating many of the universe's heavy elements. During the explosion, extreme temperatures and pressures allow atomic nuclei to combine into heavier forms. Elements like gold, uranium, and iodine are forged in these fleeting moments. Once formed, they are scattered into surrounding space, mixing with gas and dust. Over time, this enriched material becomes part of new stars and planetary systems. Without these stellar deaths, the universe would lack the diversity of elements needed for complexity. Every solid object, every metal, and many essential materials trace their origins back to these ancient stellar explosions. The elements that make up the human body were created long before Earth existed. Carbon, oxygen, iron, and calcium were forged inside stars and released through stellar winds and explosions. Over billions of years, this material drifted, cooled, and gathered again. Eventually, it became part of the cloud that formed our solar system. This connection links living beings directly to cosmic history. The atoms in your body have traveled vast distances and endured extreme conditions. They are not separate from the universe, but shaped by it. This shared origin quietly ties human life to the long story of the stars. Stellar explosions do not mark a final conclusion, but a continuation of an ongoing cycle. The material released by dying stars enriches galaxies, making future generations of stars more complex than those before. Over time, galaxies become layered with history, each generation building upon the last. Stars form, shine, change, and return their substance to space. This cycle has repeated for billions of years and continues still. Nothing is wasted. Matter is reused, reshaped, and redirected endlessly. This slow, patient recycling ensures that the universe remains active and evolving, preparing the conditions for everything that follows in the cosmic story. Black holes form when certain massive stars reach the end of their lives and collapse under their own gravity. After nuclear fuel is exhausted, nothing remains to support the star's core. Gravity takes over completely, compressing matter into an extraordinarily small and dense region. The collapse happens quietly at first, hidden deep within the star before revealing its presence through powerful effects on surrounding space. Though black holes themselves emit no light, their influence shapes entire regions of the universe. They are not cosmic destroyers roaming freely, but remnants formed through predictable processes that follow naturally from the life cycles of massive stars. A black hole's gravity becomes so intense that beyond a certain boundary, light itself cannot escape. This boundary is known as the event horizon. Crossing it does not produce an explosion or sudden destruction. Instead, it marks a point of no return where all possible paths lead inward. To a distant observer, matter approaching this boundary appears to slow and fade. From within, physics enters a realm we cannot yet fully describe. The event horizon defines what we can observe and what remains hidden. It represents a quiet threshold between the known universe and regions beyond our current understanding. Many black holes rotate, carrying with them the angular momentum of the stars that formed them. This rotation causes space-time itself to twist around the black hole in a phenomenon known as frame dragging. Nearby matter and radiation are pulled into swirling paths, unable to remain still. The faster the black hole spins, the stronger this effect becomes. Rotation adds structure and complexity to these otherwise invisible objects. It shapes how matter falls inward and how energy escapes in other forms. Through rotation, black holes influence their surroundings far beyond their immediate boundaries, subtly reshaping space itself. At the centers of most large galaxies reside supermassive black holes containing millions or even billions of times the Sun's mass. These objects formed early in cosmic history and grew alongside their host galaxies. Though enormous, they occupy surprisingly small regions of space. Their presence is revealed through the motion of stars and gas orbiting nearby. Rather than constantly consuming everything around them, these black holes often remain quiet for long periods. Yet, when they do feed, they release tremendous energy. Their steady influence helps regulate the structure and evolution of galaxies across vast timescales. At the center of our own galaxy lies a supermassive black hole known as Sagittarius A star. It holds millions of solar masses within a region smaller than our solar system. Nearby stars move rapidly in tight orbits, tracing the invisible object's immense gravity. Despite its size, this black hole is currently calm, emitting little energy. It rests at the Milky Way's core like a silent anchor, shaping the galaxy's structure without disturbance. Its quiet presence reminds us that extreme objects do not always announce themselves loudly. Often, their greatest influence comes through steady, persistent gravity rather than dramatic displays. Although black holes themselves emit no light, matter falling toward them can glow intensely. Gas drawn in by gravity accelerates, heats, and forms a swirling disk around the black hole. Friction and compression within this disk raise temperatures to extraordinary levels, causing the material to radiate across the spectrum. In some cases, this light can outshine all the stars in the surrounding galaxy. These luminous regions allow astronomers to detect black holes from great distances. What appears as brilliance is actually the final energy released by matter before it disappears from view, marking the edge between visibility and silence. Some black holes produce narrow jets of particles that shoot outward at nearly the speed of light. These jets are guided by powerful magnetic fields and the black hole's rotation. They extend far beyond the galaxy itself, carving paths through surrounding gas. Along the way, they heat matter, trigger radiation, and shape large-scale structures. Though launched from regions smaller than our solar system, these jets influence areas millions of light-years across. Their reach demonstrates how compact objects can affect enormous volumes of space. Through these jets, black holes leave visible imprints on the cosmic environment. Near a black hole, gravity becomes so strong that it affects the flow of time itself. Clocks closer to the black hole tick more slowly compared to those farther away. This effect is not theoretical, it has been measured in weaker gravitational fields near Earth. Around black holes, it becomes extreme. To a distant observer, processes near the event horizon appear frozen and stretched. This slowing of time is a natural consequence of space-time's structure. It reveals that time is not universal or constant, but responsive to mass and motion, gently reshaped by gravity's influence. Space and time are not separate entities, but woven together into a unified fabric called space-time. Objects with mass and energy curve this fabric, guiding the motion of everything around them. Planets follow curved paths, stars orbit galactic centers, and light bends as it passes massive objects. This view replaces the idea of gravity as a pulling force with one of gentle guidance along curved routes. Space-time responds continuously to what it contains. The universe becomes a dynamic geometry rather than a static stage, quietly adjusting itself as matter and energy move through it. Gravity is best understood as the curvature of space-time rather than a traditional force. Massive objects create depressions in space-time, and other objects follow the resulting curves. This explains why planets orbit stars and why light can bend near galaxies. The effect is subtle at small scales but profound across cosmic distances. Gravity does not push or pull through emptiness. It shapes the pathways that everything follows. This elegant description unifies motion, mass, and time into a single framework. From this perspective, the universe moves not through forceful action, but through quiet geometry unfolding over time. Planets form within rotating disks of gas and dust that surround young stars. These disks are leftovers from the star's own formation, spreading outward like a thin, spinning veil. Within them, tiny particles collide and stick together, slowly growing larger. Over long periods, gravity helps these growing bodies gather more material, shaping them into planets. This process unfolds quietly and gradually, without urgency. Nothing appears suddenly. Each planet represents countless small interactions accumulated over time. As the disk thins and clears, stable orbits emerge, leaving behind worlds that carry the history of their star's earliest moments. The earliest building blocks of planets are microscopic grains of dust. These grains drift through the disk, gently colliding and occasionally sticking together. As they grow, gravity begins to assist, drawing in nearby material. Pebbles become boulders, boulders become planetary cores. This growth is uneven and patient, shaped by chance encounters and local conditions. Some regions grow faster than others, creating diversity from the very beginning. Even failures play a role, as collisions that break objects apart recycle material back into the disk. Over time, this slow accumulation transforms scattered dust into solid, lasting worlds. Not all planets remain where they form. Some migrate inward or outward as they interact with the surrounding disk or with other planets. These movements can be slow and steady or sudden and dramatic. A planet may drift closer to its star, becoming intensely heated, or move outward into colder regions. Migration reshapes planetary systems, altering orbits and sometimes ejecting worlds entirely. These journeys occur over millions of years, guided by gravity and momentum rather than intent. Migration explains why many planetary systems look very different from our own, revealing that stability often emerges from long periods of motion and change. Planetary orbits are not always neat circles. Many follow elongated paths that carry them closer to their star at one point and farther away at another. These shapes arise from gravitational interactions with other planets or passing stars. Over time, orbits can stretch, tilt, or shift entirely. These variations influence climate, temperature, and internal activity. Even small changes can accumulate, slowly reshaping a system's architecture. Orbits reflect a system's history, preserving traces of past encounters. Each path tells a quiet story of balance and disturbance, showing that motion in space is rarely simple but often beautifully complex. Some planets drift through space without orbiting any star. These free-floating worlds are thought to form in planetary systems before being ejected by gravitational encounters. Once released, they travel alone through the darkness between stars, illuminated only faintly by distant light. Their surfaces may freeze, yet internal heat can linger for billions of years. Though isolated, they remain complete worlds with complex interiors. These wandering planets suggest that planetary formation is robust, producing worlds even when long-term stability fails. They remind us that not all planets belong to systems, and that solitude is also part of the cosmic landscape. Thousands of planets have been discovered orbiting stars beyond our solar system. These exoplanets are detected not by sight, but by subtle effects they produce. Some dim their star's light as they pass in front of it. Others cause gentle wobbles through gravitational pull. Each discovery adds to a growing census of worlds throughout the galaxy. Though these planets appear as points of data, they represent real places with structure and motion. The steady accumulation of discoveries reveals patterns and surprises, expanding our understanding of how common planets are and how diverse their forms can be across the universe. Planets that orbit stars other than the Sun are called exoplanets. The term simply means outside our planetary system. These worlds vary widely in size, composition, and temperature. Some resemble gas giants, others rocky surfaces, and many fall between familiar categories. Exoplanets challenge assumptions formed from studying only our solar system. Their variety shows that planetary formation can follow many paths. Each newly identified exoplanet broadens the range of known possibilities. The name itself reflects a shift in perspective, from seeing planets as rare companions to stars to recognizing them as common outcomes of cosmic processes. Some exoplanets are larger than Jupiter, the biggest planet in our solar system. These massive worlds contain thick envelopes of gas surrounding dense cores. Their gravity strongly influences nearby space, shaping orbits and disk material. Many orbit very close to their stars, where intense heat inflates their atmospheres. Despite their size, they can remain surprisingly light, puffed outward by radiation. These giants reveal how planetary mass and environment interact. Their existence helps astronomers test theories of formation and migration. By studying such planets, we learn how size alone does not define a world's structure or behavior. Not all exoplanets are large. Many are smaller than Earth, with masses and sizes that suggest rocky compositions. These planets are harder to detect, yet increasingly common in surveys. Some may have thin atmospheres, others thick envelopes of gas. Their surfaces and interiors remain unknown, but their existence shows that Earth-sized planets are not rare. These smaller worlds occupy a quiet but important place in planetary systems. They form close to their stars and far away, in warm regions and cold. Their presence deepens the sense that our planet's size is not unique in the galaxy. Many exoplanets orbit extremely close to their stars, completing full orbits in just days. At such distances, gravity locks their rotation and heat becomes intense. Their atmospheres expand, surfaces glow, and winds race at tremendous speeds. These worlds experience conditions far beyond anything in our solar system. Their proximity reveals how planets respond to extreme radiation and tidal forces. Studying them helps astronomers understand the limits of planetary survival. These close-orbiting planets illustrate how varied planetary environments can be, even within the same galaxy, preparing us to explore stranger worlds still waiting ahead. Some planets become tidally locked to their stars, meaning one side always faces the light while the other remains in darkness. This happens when gravity gradually slows a planet's rotation until it matches its orbit. Over long periods, the planet settles into stillness, presenting the same face forever. On such worlds, the day side can be intensely hot while the night side grows cold and quiet. Between them lies a gentle boundary where temperatures may balance. Tidal locking shows how gravity shapes not only orbits, but the rhythm of a planet's experience, turning motion into permanence. On some planets, heat becomes so extreme that solid rock can melt and flow like liquid. These worlds orbit close to their stars, absorbing enormous amounts of energy. Their surfaces may glow faintly, reshaped constantly by tides and heat. Instead of oceans of water, they host seas of molten stone that rise and fall slowly. Vaporized minerals can form thin atmospheres, drifting from the hot side toward cooler regions. These planets reveal how familiar materials behave under unfamiliar conditions. They remind us that planets are shaped not only by composition but by where they reside in relation to their stars. Some moons may hide vast oceans beneath thick shells of ice. Though their surfaces appear frozen and still, internal warmth keeps liquid water moving below. This heat can come from tidal forces or leftover energy from formation. Cracks and ridges on the surface hint at activity underneath. These hidden oceans may be deeper than any found on Earth, protected from space by layers of ice. Darkness does not mean stillness here. Beneath the surface, water may circulate slowly, carrying heat and chemistry through unseen depths, expanding the idea of where active environments can exist. Moons are not always quiet companions. As they orbit their planets, gravitational forces stretch and compress them repeatedly. This tidal motion generates internal heat, which can melt rock or ice deep inside. The surface responds with cracks, ridges, and smooth plains that reveal constant change. Some moons erupt plumes of material into space, while others shift more subtly. These processes show that moons can be dynamic worlds in their own right. Their activity depends not on size alone, but on motion and proximity. Through tides, gravity transforms orbit into energy. Tidal heating allows some worlds to remain warm even far from their stars. As a moon follows a slightly uneven orbit, gravity flexes its interior like a slow, steady kneading. This friction produces heat that can last for billions of years. Ice melts, rock softens, and internal oceans persist. This warmth does not rely on light, but on motion. It creates environments shielded from the cold of space, where chemistry can continue quietly. Tidal heating expands the definition of habitable conditions, showing that energy can come from many sources, not just the glow of a nearby star. In some cases, moons display more geological activity than the planets they orbit. Their smaller size allows tidal forces to affect them more strongly. Volcanoes, shifting surfaces, and subsurface oceans can all arise from this interaction. While planets may cool and settle over time, moons remain restless due to constant gravitational stirring. This contrast highlights how motion matters as much as mass. Activity is not reserved for the largest worlds. Sometimes it is the smaller companions, caught in delicate gravitational balances, that experience the most change, revealing that dynamism in the universe often arises from relationship rather than scale. Planetary rings form when material orbits too close to a planet to gather into a single moon. Gravity prevents the pieces from merging, keeping them spread out in a thin disk. These fragments may come from shattered moons, captured debris, or leftover material from formation. Each particle follows its own path, yet together they create structured bands and gaps. Rings are not solid objects, but collections of countless individual pieces moving in harmony. Their delicate appearance masks a complex balance of forces where gravity and motion cooperate to maintain order without ever fully uniting. Saturn's main rings are composed mostly of ice mixed with dust and rock. Though they appear bright and solid from afar, they are made of countless particles ranging from grains to house-sized chunks. These rings span great distances but remain remarkably thin. Sunlight reflects off their icy surfaces, giving Saturn its iconic appearance. Over time, particles collide gently, breaking and reforming shapes. The rings change slowly, shaped by gravity from Saturn and its moons. They are temporary features on cosmic timescales, reminding us that even the most beautiful structures are part of an ongoing process. Some planetary ring systems are far larger than Saturn's visible rings, stretching across tens of millions of kilometers. These vast structures are often faint and diffuse, discovered through careful observation. They surround massive planets and contain enormous amounts of material spread thinly through space. From afar, they resemble soft halos rather than sharp bands. Their size reveals how gravity can organize matter across extraordinary distances. These immense rings challenge assumptions about scale, showing that delicate structures can exist even when stretched across regions larger than planetary orbits, quietly circling their parent worlds. Planetary systems throughout the galaxy display remarkable diversity. Some are tightly packed, others widely spaced. Some contain massive giants close to their stars, while others hold small rocky worlds far away. Moons, rings, and wandering planets add further complexity. No single arrangement defines a normal system. Instead, each reflects its own history of formation, movement, and interaction. This variety suggests that the processes that build planets are flexible and resilient. Across the galaxy, gravity assembles worlds in countless ways, creating systems that are stable yet unique, preparing us to explore even more unexpected configurations ahead. Comets are icy remnants left over from the earliest stages of planetary formation. They formed far from the Sun, where cold temperatures preserved simple ices and dust. For most of their lives, comets remain distant and inactive, moving slowly through the outer reaches of the solar system. When one drifts closer to a star, warmth awakens it. Ice turns directly into gas, releasing dust into space. This creates glowing comas and long, flowing tails. Each comet carries material that has remained largely unchanged for billions of years, offering a quiet glimpse into the solar system's distant beginnings. As comets approach the Sun, their tails form and stretch away, guided by light and charged particles. One tail follows the flow of ionized gas shaped by the solar wind. Another trails dust pushed gently by sunlight itself. These tails do not follow the comet's path but point outward, responding to invisible forces. Their shape can change from night to night as conditions shift. The glowing arcs trace interactions between radiation and matter. In these delicate structures, we see how light and energy shape objects without touch, revealing the quiet influence of forces that fill space. Comets contain organic molecules that formed long before planets like Earth existed. Within their frozen interiors are compounds built from carbon, hydrogen, oxygen, and nitrogen. These molecules assembled slowly in cold interstellar environments and were preserved as the solar system took shape. When comets warm, these substances are released into space, briefly visible before dispersing again. Studying them shows that complex chemistry arises naturally without biology. The same building blocks that appear in living systems can form in deep space, drifting quietly through time. Comets remind us that chemistry connects planets, stars, and life itself. Asteroids are rocky remnants left behind when planets were forming. They orbit stars as fragments of material that never gathered into larger worlds. Some remain unchanged since their creation, while others show signs of heating and transformation. Their surfaces record collisions and radiation over immense periods. Asteroids vary widely in composition, from metal-rich cores to primitive stone. Though often small, they preserve crucial information about planetary beginnings. Each asteroid is a surviving piece of a much larger story, moving steadily along its orbit, carrying evidence of early conditions that shaped planets and moons. Some asteroids are rich in metals forged deep within early planetary bodies. These metallic asteroids may be fragments of larger objects that once melted and differentiated, separating heavy elements toward their cores. When collisions shattered these bodies, metallic interiors were exposed and scattered. Today, these asteroids move quietly through space, dense and reflective. Studying them reveals how heat and gravity shaped early worlds. They offer direct insight into processes that normally remain hidden beneath planetary surfaces. These metallic remnants preserve a record of ancient internal structures, long before planets fully settled into stable forms. Collisions played a major role in shaping planets and moons. In the early solar system, objects moved on intersecting paths, frequently striking one another. Some impacts were gentle, allowing bodies to merge. Others were violent, reshaping surfaces or altering rotation. These encounters created moons, stripped atmospheres, and formed basins that still exist today. Though destructive, collisions were also creative, redistributing material and energy. Over time, fewer objects remained, and orbits stabilized. The scars left behind tell stories of chaos gradually giving way to order, marking the transition from a turbulent beginning to lasting structure. Meteorites are fragments of space rock that survive passage through a planet's atmosphere and reach the surface. Many meteorites formed before Earth itself, preserving material from the early solar system. Their composition reveals the conditions that existed when planets were just beginning to assemble. Some contain tiny mineral grains older than the Sun. These pieces have traveled for billions of years before arriving quietly on the ground. Studying meteorites allows scientists to hold ancient history in their hands. They serve as tangible reminders that Earth is part of a much older and wider cosmic process. Large impacts can dramatically reshape a planet's surface and internal structure. The energy released during such events melts rock, creates vast craters, and sends material far into space. Some impacts may have contributed to the formation of moons or altered a planet's tilt. Others triggered long-term changes in climate and geology. Though rare today, these events were once common. Their influence lingers in cratered landscapes and layered rock. Impacts represent moments of sudden change within long periods of stability, showing how brief events can leave marks that persist for billions of years. Planetary atmospheres can be stripped away by intense stellar winds and radiation. When charged particles stream outward from a star, they collide with atmospheric gases, giving them enough energy to escape. Planets without strong magnetic fields are especially vulnerable. Over time, this loss can thin an atmosphere or remove it entirely. These processes shape planetary evolution, influencing temperature and surface conditions. Atmospheric escape happens gradually, not all at once, altering worlds slowly. It demonstrates how stars influence their planets long after formation, quietly reshaping environments through steady flows of energy rather than sudden events. Magnetic fields help protect planets from harmful radiation. Generated by motion within a planet's interior, these fields extend outward into space, forming invisible shields. When stellar winds encounter a magnetic field, many charged particles are deflected or guided around the planet. This protection helps preserve atmospheres and reduces surface radiation. Magnetic fields vary in strength and structure, changing over time. Their presence influences long-term planetary stability. Though unseen, magnetic fields play a crucial role in shaping planetary environments, quietly standing between worlds and the constant stream of energy flowing from nearby stars. Pulsars are rapidly spinning remnants left behind after massive stars explode. Though small in size, they contain enormous mass packed tightly together. As they rotate, beams of radiation sweep outward from their magnetic poles. When these beams cross our line of sight, they appear as steady pulses of light. The rhythm can be so precise that it rivals the accuracy of the finest clocks. Pulsars turn the aftermath of stellar death into something orderly and predictable, offering calm regularity amid extreme conditions. Their steady signals carry information across vast distances, quietly marking the passage of time in space. Neutron stars compress more mass than the Sun into a sphere only about the size of a city. In this environment, atoms are crushed so tightly that electrons and protons merge, forming neutrons. The resulting matter behaves unlike anything on Earth. Gravity at the surface is immense, warping space-time and anchoring material firmly in place. Despite this intensity, neutron stars can persist for billions of years. They represent a stable endpoint for many stars, showing how the universe supports extraordinary structures without collapse, maintaining balance even at the edge of physical possibility. Inside neutron stars, matter exists in forms that remain largely theoretical. Density increases so dramatically that familiar concepts of solid and liquid lose meaning. Atomic structures dissolve, and particles interact in collective ways shaped by quantum mechanics. These conditions cannot be recreated in laboratories, making neutron stars natural experiments scattered across the galaxy. Their interiors may contain exotic phases of matter that challenge existing theories. By observing their behavior, astronomers infer properties of matter under extreme pressure. These stars quietly expand our understanding of physics, revealing how nature behaves when pushed far beyond everyday limits. As neutron stars rotate, their intense magnetic fields channel particles into narrow beams. These beams sweep through space like lighthouse lights across a dark sea. When aligned with Earth, they create pulses detected at regular intervals. Some pulsars rotate hundreds of times per second, yet maintain astonishing stability. This consistency allows astronomers to use pulsars as tools for navigation and measurement across the galaxy. Their predictable signals contrast with the violent events that created them. In the quiet repetition of their pulses, pulsars transform chaos into rhythm, offering a steady presence in an otherwise ever-changing universe. The timing of pulsar signals can be so precise that it rivals atomic clocks on Earth. Slight variations in these signals reveal subtle changes in motion, gravity, or surrounding space. By monitoring these shifts, scientists detect gravitational waves, map galactic structure, and test fundamental theories. Pulsars act as anchors of regularity, allowing measurement over vast distances. Their reliability arises from their compact mass and stable rotation. In a universe defined by change, pulsars provide a dependable reference, quietly ticking away in the darkness, marking time on scales far larger than any human system. Gravitational waves are ripples that travel through space-time itself. They form when massive objects accelerate, such as when two neutron stars or black holes spiral together. These waves stretch and compress space as they pass, carrying energy outward. Though incredibly faint by the time they reach Earth, sensitive instruments can detect their effects. Gravitational waves provide a new way to observe the universe independent of light. They reveal events hidden from view, allowing us to sense cosmic motion directly. Through these ripples, space-time quietly communicates the universe's most powerful interactions. Gravitational waves were predicted long before they were observed. Einstein's equations suggested their existence over a century ago. For decades, they remained theoretical, too subtle to measure. Advances in technology eventually made detection possible. When the first signals were recorded, they confirmed a fundamental aspect of space-time. These detections opened a new chapter in astronomy, allowing observation through vibration rather than light. The waves carried information from distant mergers, reaching Earth after traveling for billions of years. Their discovery transformed understanding without altering the universe itself, revealing truths that had always been quietly present. When black holes collide, they release enormous amounts of energy in the form of gravitational waves. These events reshape space-time itself, sending ripples across the cosmos. The merging objects vanish into a single, more massive black hole, leaving behind a fading vibration known as a ring-down. Though invisible to telescopes, the collision is recorded through space-time's response. These mergers occur far from Earth, yet their signals reach us clearly. They demonstrate how distant events can influence the fabric of the universe everywhere, linking separate regions through the shared structure of space-time. Space is filled with a faint background of radiation left over from the universe's earliest stages. This glow permeates all directions, uniform and steady. It represents light released when the universe cooled enough for atoms to form. Since then, it has traveled freely, stretched by expansion into microwave wavelengths. This radiation provides a snapshot of the young universe, preserved across time. It forms a quiet backdrop to all cosmic activity, reminding us that even empty space carries memory. The universe retains traces of its beginnings, gently glowing beneath everything that followed. The cosmic microwave background is the oldest light we can observe. It comes from a time when the universe was just hundreds of thousands of years old. Before this moment, space was opaque, filled with charged particles. When atoms finally formed, light was released and began its long journey. Today, that light appears cooled and uniform, revealing subtle patterns that reflect early structure. By studying these patterns, scientists learn how matter began to gather into galaxies. This ancient light anchors cosmic history, connecting the present universe to its earliest visible moment. Most of the universe's matter is invisible and known as dark matter. It does not emit or absorb light, making it undetectable by ordinary telescopes. Yet its presence is revealed through gravity. Galaxies rotate faster than visible matter alone can explain, and clusters remain bound by unseen mass. Dark matter acts as a quiet scaffold, shaping cosmic structures without drawing attention to itself. It gathers matter, guides formation, and holds galaxies together. Though its nature remains unknown, dark matter's influence is steady and patient, quietly shaping the universe from behind the scenes. Dark matter interacts with the universe almost entirely through gravity. It neither shines nor reflects, passing silently through space and even through ordinary matter. Despite this elusiveness, its gravitational pull is unmistakable. Stars orbit galaxies as if additional mass surrounds them, and light bends more strongly than visible matter allows. These effects reveal dark matter's distribution on large scales. It forms vast halos around galaxies and filaments between them. Though unseen, dark matter leaves fingerprints in motion and structure, guiding cosmic evolution without ever revealing its true form to our senses. Galaxies rotate at speeds that cannot be explained by their visible material alone. Stars at the edges move as quickly as those nearer the center, defying expectations. Without extra mass, these stars should drift away. Dark matter provides the missing gravity, holding galaxies together. This hidden mass extends far beyond visible boundaries, forming expansive halos. Observations of rotation curves offer some of the strongest evidence for dark matter's existence. Through these motions, galaxies reveal what cannot be seen. Their steady rotation tells a quiet story of unseen influence shaping structure across cosmic time. Dark energy is the name given to the unknown cause of the universe's accelerating expansion. Unlike gravity, which pulls matter together, dark energy appears to push space apart. Its effects become noticeable only across immense distances. As the universe grows, dark energy's influence increases, gradually overcoming gravitational attraction between galaxies. Though poorly understood, dark energy dominates the universe's overall behavior. It sets the long-term fate of cosmic expansion. In this way, most of the universe's future is guided by a force we cannot see or fully describe, quietly directing the largest-scale motion of all. Only a small fraction of the universe is made of matter we can directly observe. Stars, planets, gas, and dust account for a tiny percentage of the total. The rest consists of dark matter and dark energy. This means that most of the universe operates beyond direct human perception. Astronomy becomes an exercise in inference, using motion, light, and structure to understand the unseen. Despite this limitation, patterns emerge clearly. The universe behaves consistently, even when much of it remains hidden. This unseen majority reminds us that reality extends far beyond what our senses can detect. Astronomy allows us to study objects billions of years old simply by observing their light. Because light takes time to travel, distant objects appear as they were long ago. Telescopes become time machines, revealing earlier chapters of cosmic history. Each observation captures a moment preserved across space. By comparing light from different distances, astronomers reconstruct the universe's growth and change. This ability to see across time transforms observation into storytelling, where light serves as the narrator. Through careful measurement, the universe reveals its past gently, one photon at a time. Telescopes observe much more than visible light. The universe emits radiation across a wide spectrum, from long radio waves to energetic gamma rays. Each wavelength reveals different physical processes. Visible light shows stars and galaxies, while other wavelengths uncover hidden structure. By combining observations across the spectrum, astronomers build a fuller picture of cosmic activity. This approach reveals layers of complexity invisible to the eye alone. Light becomes a messenger in many forms, each carrying unique information. Together, these signals allow the universe to be understood more deeply, even as it remains vast and mysterious. Infrared light allows astronomers to see through dust that blocks visible wavelengths. Star-forming regions often remain hidden behind thick clouds, yet infrared light passes through, revealing newborn stars. Cooler objects, such as brown dwarfs and distant planets, also glow in infrared. By observing this light, astronomers study regions otherwise concealed. Infrared observations extend our view into colder and darker environments, showing that activity continues even where visible light fades. This gentle form of observation uncovers quiet processes unfolding behind cosmic curtains, expanding our understanding of how stars and planets emerge. Radio waves reveal vast reservoirs of gas between stars and galaxies. These emissions trace hydrogen and other elements that form the raw material for future stars. Radio observations map structures spanning enormous distances, including spiral arms and intergalactic filaments. Because radio waves pass easily through dust, they provide clear views of otherwise obscured regions. This information helps astronomers understand how matter flows through the universe. Gas moves slowly, gathering and dispersing over millions of years. Through radio astronomy, these invisible motions become visible, showing how the universe continually reshapes itself through gradual processes. X-rays expose the universe's most energetic and extreme environments. They originate from hot gas, violent collisions, and matter falling toward compact objects. X-ray observations reveal black holes, neutron stars, and superheated clusters of galaxies. These wavelengths trace regions where gravity and energy interact intensely. Though dangerous to life, X-rays provide crucial information about high-energy processes. By studying them, astronomers explore conditions far beyond ordinary experience. These observations balance the gentler wavelengths, completing the cosmic picture. Through X-rays, the universe reveals its most intense moments, still governed by the same underlying laws. On the largest scales, matter in the universe forms a vast structure known as the cosmic web. Galaxies gather along enormous filaments of dark matter and gas, stretching across hundreds of millions of light-years. Between these filaments lie vast voids, regions with very little matter at all. This structure emerged slowly as gravity amplified tiny differences left over from the early universe. The cosmic web gives the universe a gentle architecture, neither random nor rigid. Everything moves within it gradually, guided by gravity's patient influence, creating a quiet order that spans incomprehensible distances. Galaxies are not scattered randomly through space. They tend to line up along the filaments of the cosmic web, tracing paths shaped by dark matter. These filaments act like invisible highways guiding the flow of gas that feeds star formation. Over time, galaxies drift slowly along these structures, drawn toward clusters where gravity is strongest. The arrangement is subtle but consistent across the observable universe. Even on the grandest scales, matter follows patterns. This alignment reveals how unseen forces shape visible structure, showing that galaxies are part of something far larger than themselves. Between the filaments of the cosmic web lie immense voids, regions where very little matter exists. These voids can span hundreds of millions of light-years, containing only sparse galaxies and thin gas. They are not empty, but profoundly calm. Matter once present was slowly drawn away toward denser regions, leaving behind these open expanses. Void regions help scientists understand how gravity redistributes matter over time. Their stillness contrasts with the activity of clusters and filaments. Together, voids and structures form a balanced cosmic landscape shaped by long, gentle processes. Gravity can bend light as it travels through space. When light from a distant galaxy passes near a massive object, its path curves slightly. This effect, called gravitational lensing, was predicted by Einstein and later observed. The bending can distort, stretch, or even duplicate the appearance of background objects. Though subtle, lensing reveals the distribution of mass, including dark matter, along the light's path. Through this bending, gravity quietly alters how the universe appears, allowing astronomers to map invisible structures by observing how light responds to unseen mass. Gravitational lensing can act like a natural telescope. When alignment is just right, massive objects magnify distant galaxies that would otherwise be too faint to detect. Light is stretched into arcs, rings, or multiple images, revealing fine details from the early universe. This magnification allows astronomers to study galaxies formed billions of years ago. Lensing requires no instruments built by humans, only gravity itself. It demonstrates how the universe provides its own tools for observation. Through these quiet distortions, distant light becomes accessible, offering glimpses into eras long past. Because light travels at a finite speed, astronomy is inherently historical. Observing distant objects means observing earlier versions of the universe. Nearby stars appear relatively current, while distant galaxies show youthful forms shaped by early conditions. This layered view allows astronomers to reconstruct how structures evolved over time. By comparing objects at different distances, the universe's growth becomes visible. There is no single moment being observed, but many overlapping eras. Astronomy gently weaves these moments together, turning the sky into a record of change that unfolds slowly across billions of years. Every photon carries information about where it came from and what it encountered along the way. Its color, energy, and direction reflect conditions at its origin and interactions during its journey. By decoding these properties, astronomers learn about temperature, composition, motion, and gravity. Light becomes a messenger that requires no interpretation beyond careful observation. Even after traveling for billions of years, photons preserve their story. This reliability allows knowledge to pass across vast distances. Through light alone, the universe communicates its structure, history, and behavior in a steady, patient language. The night sky is filled with ancient light that has traveled for immense spans of time. Each point of light represents a moment preserved, arriving long after it was emitted. Some stars may no longer exist, yet their light continues onward. The sky becomes an archive rather than a snapshot, containing records of many different eras at once. Looking upward is not simply observing space, but engaging with time. This layered view transforms darkness into depth, reminding us that even stillness contains motion, and even silence carries stories from the distant past. Despite centuries of study, humanity has explored only a small fraction of the universe's full complexity. Each discovery reveals new questions and deeper layers of structure. The cosmos remains vast, with many processes still unknown. This limitation does not diminish understanding, but gives it context. Knowledge grows slowly, built from careful observation rather than certainty. The universe invites patience rather than urgency. What we know continues to expand, yet always within a much larger unknown. This balance between insight and mystery keeps astronomy grounded, reminding us that curiosity can remain gentle and open-ended. Much of the universe remains unexplored and perhaps fundamentally unknowable. Dark matter, dark energy, and conditions at extreme scales challenge current understanding. Yet patterns remain consistent and laws hold steady across distance and time. The unknown is not chaos, but uncharted structure. Astronomy accepts uncertainty as part of its foundation. Rather than demanding complete answers, it traces relationships and behaviors. This acceptance creates calm rather than tension. The universe does not rush to reveal everything at once. It unfolds slowly, allowing understanding to deepen gradually, one careful observation at a time. Astronomy weaves together physics, chemistry, time, and motion into a single story. The same laws that govern falling objects on Earth shape the movement of galaxies across space. Light, matter, and energy follow consistent rules no matter how far they travel. This unity allows astronomers to understand distant worlds using principles discovered close to home. Across immense distances, the universe behaves with remarkable coherence. Nothing stands apart. Each process connects to another, forming a continuous fabric of cause and effect. In this way, astronomy becomes a quiet reminder that all things belong to one unfolding system. The physical laws observed on Earth appear to operate everywhere in the universe. Atoms behave the same in distant galaxies as they do nearby. Gravity bends space-time consistently across vast scales. Light follows predictable paths no matter how far it travels. This reliability allows scientists to interpret signals from the most remote regions of space. The universe does not reinvent itself from place to place. Instead, it expresses the same principles endlessly, creating harmony across distance. This consistency provides stability in an otherwise vast and changing cosmos, allowing understanding to grow slowly and with confidence. The building blocks of life form naturally in space long before planets develop living systems. Simple molecules assemble in cold clouds, on dust grains, and within icy bodies. Over time, these compounds grow more complex through gentle interactions. When stars and planets form, this chemistry becomes part of their structure. Life does not require rare ingredients, only the right conditions over long periods. Astronomy reveals that the universe prepares its materials patiently, without intent or urgency. This quiet preparation suggests that complexity arises naturally when time, energy, and matter are allowed to interact freely. The atoms that make up your body are the same atoms found in distant stars and galaxies. Hydrogen, carbon, oxygen, and iron follow the same rules everywhere. These elements were shaped by stellar processes long before becoming part of Earth. Over time, they were recycled through stars, planets, and living systems. Nothing about them is unique to one place. This shared composition creates a subtle connection between all matter. You are not separate from the universe, but formed from it. Every breath and heartbeat echoes processes that began far beyond this planet. Stars will continue to form long after human history has passed. Cold gas will collapse, ignition will occur, and new light will appear in distant regions of space. Some stars now shining will persist for trillions of years. Others will end and give rise to new generations. The universe does not pause or conclude. It moves forward slowly, without regard for short-lived moments. Human time occupies only a narrow window within this vast progression. Yet even within that brief span, we are able to observe and understand parts of this ongoing stellar cycle. As the universe continues to expand, distant galaxies will gradually drift beyond our observable reach. Their light will stretch and fade, becoming too faint to detect. Over immense timescales, the visible universe will appear quieter and more isolated. This change does not happen suddenly, but unfolds gradually. What is visible today will not always remain so. Astronomy captures a particular era, one in which distant structures are still accessible. This fleeting clarity adds meaning to observation, reminding us that the universe itself changes what can be known, not through loss, but through evolution. Cosmic events unfold over timescales far beyond individual lives. Galaxies evolve over billions of years. Stars are born, change, and fade across spans longer than civilizations. These rhythms operate independently of human presence, yet they are not distant in principle, only in scale. Astronomy bridges this gap by translating slow processes into understanding. Through observation and theory, long durations become comprehensible. The universe teaches patience through its timing. Nothing is rushed, everything proceeds at its own pace, reminding us that rest and stillness are natural states within a vast, enduring system. Though the universe is vast, it is not beyond comprehension. Patterns repeat, laws remain stable, and observations accumulate meaningfully. Understanding does not require control or completion. Partial knowledge is still valuable. Astronomy progresses by listening rather than forcing answers. Each discovery adds clarity without closing the story. This approach mirrors the universe itself, which reveals structure gradually. Comprehension grows through calm attention rather than urgency. In this way, understanding becomes a form of quiet participation rather than mastery, allowing curiosity to remain open and gentle. Every astronomical discovery becomes part of a shared human story. Observations made in one place inform understanding everywhere. Knowledge accumulates slowly, passed between generations. Each contribution adds context rather than finality. Astronomy is not a collection of isolated facts, but a continuous narrative shaped by curiosity and care. The universe does not belong to any one observer. Its story unfolds collectively across cultures and centuries. This shared pursuit connects individuals through time, linking quiet moments of observation to a larger tradition of listening to the cosmos. You are made of matter shaped by stars and time. The atoms within you were formed in ancient stellar processes and carried across space before becoming part of Earth. Your existence rests on events that unfolded long before memory. In this way, you are not separate from the universe, but an expression of it. The same forces that shaped galaxies shaped you. This connection does not require effort or awareness. It simply exists, quietly, reminding you that rest is not withdrawal, but a return to the larger rhythm that has always carried you. Now let the vastness soften into stillness. The universe continues its slow unfolding without needing anything from you. Stars will rise and fade in their own time. For now, allow your breath to settle, your thoughts to drift, and your body to rest within this quiet, patient cosmos. Good night.